periodicity part 2 now. And I added some more sections. So it's 712, 713, 14, 15, and 16 in your notes. Excuse me. Let me get the hiccups, so I gotta be careful. All right. So I just told you about the periodic law that says that when the atoms of an element are arranged by electron configuration, each and then in the groups, when they are arranged by groups of the same electron configuration, the same valence electron configuration, their properties recur periodically. So that means that if I find what are some properties of like well, I mentioned it before, but what are some properties that nitrogen has? Well, you expect that if you go down a period, phosphorus or arsenic, antimony would also have the same properties, or very similar. Not all the same, like but similar. Okay, so let's see here. So let me move on. So now we're 7, for sure we're 13 by now. It talks about the radius of atoms and ions. Now, okay, first there's a little definition at the beginning about what do we mean by radius of an atom. It's kind of hard to know the radius of an atom because you would think it's from the nucleus to wherever the outermost electron would happen to be for that atom. If I draw an electron cloud here, you might say, well, the electrons never go past this part, so I guess that will be the radius. And that's okay to think of that as the radius. The radius is from the center to the outermost part of the circle or the orbit of the highest electron. Well, the thing is, we have no way to really detect that. That thing's moving around so fast, that little electron particle. So what they do to find the radius, and they call it the covalent radius. Now, okay, when you calculate the radius the way I'm going to show you, it will be the covalent. And you're not going to calculate anything. I should reword that. When scientists determine the radius of an atom, the way I'm going to tell you, we call this the covalent radius. But for all purposes, you can think of it just being from the center to the outermost electron. What they do is they take two atoms that are bonded together. Like let's just say I have a hydrogen atom bonded to another hydrogen atom. Okay? Now, what they do is they say, well, where's the nucleus of this one and where's the nucleus of that one? And then they measure between the two nuclei of hydrogen. So they'll take H2 molecule, then they'll say, okay, from hydrogen to hydrogen, nucleus to nucleus, this distance, and it's usually in nanometers, they'll calculate it and they'll take half of that. So half the distance between two nuclei is the radius. See, it's the same thing. It just gives them a way to find it. Like they can from doing analysis, spectral, or some kind of either mass spectrometer or whatever it would be. I don't know all the technology they would use, but from analyzing this, they can determine where that nucleus is, how far apart they are. Half of that they call the radius. So that's the way they do it. You're not going to have to really do that yourself, but especially with AP, you might have to sometimes explain that. So we call it the covalent radius, but we can just think of it as the radius of the atom, and I'll say radius a lot. So if I wanted to get, carbon, then it would be, a carbon bonded to another carbon atom, and then you take half the distance between the nuclei there. Okay, so, all right. Well, there's a pattern on the periodic table I'm going to show you, and I'm going to explain how it goes in the period and in the group. Oh, and by the way, the word covalent is it's a bond between two atoms where they share electrons. Now, you might remember an ionic bond is one where one atom, like sodium, gives up an electron. It becomes Na+1. And it joins to chlorine. Well, it starts out at chlorine, then chlorine gains an electron and becomes Cl-1. So Na+1, Cl-1, that's an ionic bond. We've told you that. Well, covalent bond is when you have, generally it's two non-metal atoms, and they share electrons. And that's going to be in the next chapter, so I'm jumping ahead. But they give the word here, covalent radius. So two covalently bonded atoms. All right. Now, what will I do here? Okay, so the first trend, I can see my notes. I need to move that down into here. I should have put a number 1 by it. One pattern is from left to right across a period, what happens. What I'm going to do is I'm going to show you on the chart. I'm going to just draw, I'm just going to look at lithium. Then I'll say beryllium. Now I'm not going to be perfect on this. Boron, carbon, nitrogen, oxygen, fluorine. I'll just try and draw this and show it to you. So let's just start off with an atom like this size. Then I move to beryllium, and look what's going to happen. Uh-oh, I might have exaggerated too much. Okay. Then boron, then carbon, then nitrogen, then oxygen, then fluorine. What is happening as you move from left to right across the chart? The radius gets smaller. Okay, so the radius decreases as you go from left to right in a period. So that means that sodium or chlorine, what's going to be the smaller atom? Chlorine. What's the larger atom? Sodium. What about between aluminum and phosphorus? Which one is larger? Aluminum. And which has a smaller radius? Phosphorus. Okay, so pretty much any period. Now again, you can find some exceptions in here and there, and we'll talk about some things that happen as well. But that tells you the general trend for the radius. Now, why is that happening in a period? Okay. The main reason is this, because if you think about it, when I start with lithium, lithium has a nucleus of +3, and then beryllium's +4. Let's just think about that for a minute. It has +3 nucleus, and then don't forget the electrons that it holds in with it. The electrons have a -3. So let's just kind of think of it, a +3, -3. I like to think about like a balloon, actually. And in a balloon, imagine that if I blew, I don't have one right that I can see quick enough to get it, but imagine that the rubber part of the balloon, you blow it up, is like the outer part, the electron. Outer part, electron negative. And then the very center of the balloon in the air, where there's nothing touching it, would be the positive. So what we're saying is, okay, if I have a +1 nucleus, and I have a -1 charge, all the balloons -1, there's sort of a size or a balance there between those two. Now, it's actually can be due also to what's called this equation, and you've seen it before. It's called Coulomb's law. And I don't do a lot to explain about it, but I just want you to know this. This is a number constant. You don't have to even worry about it. But this is the energy of attraction between two particles. Well, the two particles, two charges actually, Q stands for charge. The charge, +1 charge could be this one, and -1 could be that one. Okay? Then R would be the radius, and you could square it. How far? Now, here's the deal. So if this is +1 and that is -1, think about the attraction. Let's mainly focus on this part right here. Think about how much they would attract to each other. Okay? But if I could turn another one up to greater, +100, and make that -100 on the outside, would you expect that balloon, if the balloon skin or the rubber part was -1, +1, and +1 for the nucleus inside it? But another balloon, if it was -100 and +100, would you expect it to be larger, smaller, or the same? Well, it should be smaller, pulled in a lot closer. So it should be like this, like, wow, that's going to really pull in all those electrons. The positive and the negative are going to pull them in greater. You'd expect that to be the case. Well, I don't know if that's the best example to think about, but that is what happens. If all things else are pretty much unchanged, even if I add another positive charge, another negative charge, it's going to get smaller, smaller, smaller. Okay, so that's what's going on. The radius is about the same. Well, I know it's funny. We're talking about the radius. How can it be about the same? But I'm just saying the vicinity. If I add one proton into here, I make beryllium. If I add an electron on the outside, the electron does almost nothing, to the size of the atom because the electrons are so small. So if they were left alone, you expect it to be about the same. But since there's a greater positive, that ends up pulling in the shell closer. Now that's going to be pretty much a #1 priority in most every case. if the nucleus is greater, it's usually going to be it gets smaller. If the nucleus is greater between two things you're comparing, usually that atom is smaller. But now, here's the technical rule is, because they're being added to the same sublevel, all these outer electrons are at the n equals 2 level, or shell. Sometimes the word shell is used. So, I'm going to read the rule for you here. When you move from left to right on the chart, what does it say? From left to right across a period, each element has a smaller radius than the one before it. Why? Number 1, the nuclear charge increases. 2, each additional electron is added into the same outer energy level or valence shell. And it's very good when you're explaining this to tell me the number. Like lithium and beryllium. Why is beryllium smaller than lithium? Because the bottom line is lithium has a greater nuclear charge than... beryllium is smaller. Sorry. Because beryllium has a greater nuclear charge than lithium. And you ought to draw a diagram. I'm telling you, especially AP for essays, draw it. Draw a little circle. Lithium is positive 3 nucleus, negative 3 for the electrons. 3 electrons, negative 3 total charge. Beryllium has a positive 4 nucleus, 4 electrons there. Now, when you add more electrons, generally they would interfere with each other, and they would not want to be so close together. But since you have a stronger nucleus, that pulls them in closer. So the nucleus is the reason why it gets smaller. That's the main reason. The nuclear charge is greater, and because they are both at the same energy level shell, n equals 2. So greater nuclear charge, that's actually number 1 on the list, and that's number 2. And the electrons are added to the same energy shell, therefore the nucleus pulls the electrons in. Then I put a third one. I just wrote the electrostatic attraction between nucleus and outer valence electrons increases. As I mentioned, that's kind of the Coulomb's law, but this is probably better to go with these two. Now, it happens all the way across the chart. So for boron, if you look at boron, its nuclear charge is positive 5. So we get positive 5, then 6, then 7. I can't even fit this in here. 8, then positive 9 for fluorine. So, but notice this, all the electrons are added at the same shell. See, remember, lithium electron is 3s1. Now remember, it's 2s1. 2s1. Lithium is 1s2, 2s1. So it's like, actually, it could be good to talk about or to show the valence configuration, helium. So for lithium, it will be helium 2s1. Beryllium will be helium 2s2. Boron will be helium 2s2, 2p1. Then 2s2, 2p2. And all the way up to helium 2s2, 2p6. So what's going to be happening, AP students, is, and it's actually going to happen in general also, but in AP, you'll have to give a more detailed essay answer and than you would have to do in general. Honors would also need to be careful with this as well, too. So here's the deal. The main question will be, which atom has a larger radius? And we'll say like lithium or beryllium. Or which atom has a smaller radius? Boron or fluorine? And explain why. So first you'll know, well, fluorine has a smaller one. You'll know that part easy. Why? All right, because, as I said, fluorine has a greater nuclear charge. Fluorine has a nuclear charge of positive 9. Boron has a nuclear charge of positive 5. Okay? So fluorine is greater. Next, the outermost electron of fluorine, or outermost electron shell, is 2p6. It's 2s2, 2p6. They're all at the n equals 2 level. For boron, the outer electrons are also at the n equals 2 level. 2s2, 2p1. So, since they're the same level, meaning that, disregarding the nucleus, it would be about the same size. Well, because they're at the same level, the greater nuclear charge of fluorine pulls it in. I hate to say that disregarding the nucleus, they'd be the same size. That's not really good for me to say that, because electron repulsions can occur, and I'm going to talk about that later on. When you add more electrons, they don't like to be together. They want to move apart. but the nucleus wins out. That's the way I needed to state that. I'm sorry, I kind of contradicted myself when I've been saying that earlier about nucleus and outer electrons. But if the electrons are in the outer shell, as I move along, the electrons, they want to interfere with each other as I'm adding more and more electrons. Like, yeah, here I have 3 valence. Then here I have, the 4, well, not 3 valence, but 3 electrons. Here I have 4 electrons. Here I have 5 electrons, then 6 electrons. Adding more and more electrons, they're going to have more negative repulsion to each other. But since you have a greater nucleus, it pulls them in, and that wins out in a period. So left to right, atoms get smaller for that reason. Okay, I know you're like, oh gosh, what is that? Now, let's talk about what happens in a group. And actually, before I might keep that there. Helium, 2s2, 2p6. Okay. Let me draw these over again. So I'll try hard. That should be smaller than that one. Okay, then a little smaller, and smaller, and smaller, and smaller. Okay. Now, I'm going to show you a little diagram that will probably help you quickly remember a lot of this, I hope. And it is this. Though it's not perfect, I'm going to draw a circle, a little smaller, a little smaller, a little smaller, a little smaller, a little smaller. Now I'm going to go down, and now look what I'm going to do. What in the world is happening now? I'm going to run off the board. You can't see it all. But I'm adding another circle each time. Well, as you go down a group, atoms actually get larger. And you'll see why, and that's the main reason. It says, okay, for example, lithium would look like this. But now if I go below lithium, notice I'm going to add another shell. Now technically, actually, to be most technical, lithium's electrons, we already said, are at n equals 2. So really that means there's an n equals 1 inside there in the middle. So they already had a little circle in the middle. You don't really have to draw that. Sometimes you might want to draw that and show it. I'll just put it in there. But now when I go down, the point is, lithium has electrons at level 1, 1s2, then level 2, 2s1. 1s2, 2s1, okay? They all have 1s2 full. The green will be like the 1s2. Well then, when you move from lithium on the chart, and I go down to sodium, we've got the 1s2, 2s2, or we ought to say n equals 1, n equals 2, n equals 3. We've shown you that before. N equals 3. Okay, and that would be for, we just said sodium. So that would be Na, sodium. And then if I go down again, do I have room? Yeah, that would be like the last one that fits. That would be K, potassium. Well, the same thing I did here is true in all of these others as well. In fact, I don't want to draw all of them, but this little, I can draw that diagram smaller in a minute. But like as I go down here, the atom below fluorine is larger, one ring larger, another ring larger. Or shell is a better name for it. Okay, so that's the main reason. So let's think about the 3 things. Always think about, number 1, what's the nuclear charge? When you're comparing 2 things, nuclear charge, you might want to write down the outermost, the electron configuration. I shouldn't call it that. The valence electron configuration, the short form configuration. I don't know why I said it that way. So write down, what is the nuclear charge? What is the short form electron configuration? Where are the outermost electrons at level n equals 1, n equals 2, n equals 3? Those are the 3 main things you always want to do. I was telling you over here, if I compare boron and fluorine, you can draw a little diagram, but be aware of what's the nuclear charge of boron, positive 5. Fluorine, positive 9. What is the short form electron configuration of boron? Helium 2s2, 2p1. Or for fluorine, helium 2s2, 2p6. Then the third thing, are those outer electrons at n equals 1, n equals 2, n equals 3. And here, obviously, these are all at n equals 2, n equals 2. So the outermost shell, n equals 2. All right, those are the main things you want to look at. And for this section. Okay, so what would be a larger atom? Lithium or potassium? Okay, well, what you do is, if I draw the picture, you can say, well, obviously, potassium's larger. What's the reason? Because the outermost electrons of potassium are located at n equals 1, 2, 3, 4. The N equals 4 level. The outermost electrons of lithium are at the N equals 2 level. How would I know that? I would have to write down the short form. And I should do that. I should have done that first. Lithium, we've been doing it already. Lithium is helium, 1s2, 2s1. But potassium would be, go back to argon, 4s2. No, not 4s2. No, I'm sorry. Wait, what in the world did I do? That is not the... bad fella. That's not the short form. Helium 2s1 and argon 4s1. Sorry about that. Okay, so yeah, I should have done what I'm telling you to do. I should have write it down on the paper. Write the short form configuration. And it tells you the outermost electrons of lithium are at the N equals 2 level. Helium 2s1. 1 electron in the outer shell, N equals 2. Potassium also has 1 electron in the outer shell, but it's farther from the nucleus at N equals 4. It's farther away. Now, what about this thing about the nuclear charge? Well, the nuclear charge of lithium is positive 3, and the nuclear charge of potassium is 19. I can't read because my numbers are getting rubbed off on the side of it from me holding the chart so much. Nuclear charge, or I can do this, Z, atomic number, nuclear charge is positive 3, nuclear charge is positive 19 for potassium. Okay, so it almost seems to contradict the minute that you think, wait a minute, you said the greater nuclear charge means it's going to make the atom smaller. That's only true when the electrons are at the same outer valence shell. But when it's at a shell farther away, it's larger because of a theory called shielding. They call this the shielding effect. Now, here's what it says. Even though there's a very, very strong nucleus right here in potassium, it does positive 19 is a lot stronger than positive 3. Well, even though it's stronger, the electron on the outermost shell, the 4s1 electron, does not experience the full nuclear pull that it would feel because it's blocked by the inner shells. Here's how I like to always tell this story. All right, let's just say that you were one night, you're driving like real late or whatever, maybe some friends of yours, and you're like, hey, you've been out to, I don't know, maybe you were in Arizona and you're going to drive back to California, LA or something. You're going to do it late at night when there's not much traffic. And everybody's kind of tired. You're driving along, through the desert, and you notice, you look and you see, what in the world is that? You stop and you see all these wet tacuaches running across the road, like a big herd of them, wet, smelly tacuaches. Okay? And they're running across the road. You stop, and it's real dark, and you're the only car on the whole highway. Like, what in the world is this? Then you look over, and one of the tacuaches starts to, like, you look at a tacuache, is that little animal, that possum animal, possum. Opossum. Okay, but it's in Spanish. So you look over there and you see the tacuaches. One of them starts a fire, like maybe it has like some matches or a lighter in his little mouth, or like this, and it starts a fire. And then you notice all the tacuaches. Okay, so I'm going to draw a little fire for you here on the. Maybe I'll draw it right here. So it starts a little fire. We'll call that the fire. Then all of the tacuaches start to line up and stand around the fire. Now, the tacuaches are smelly, kind of like the Hog Hotel. They're smelly. They detract. They don't want to stand near each other. Like, oh gosh, I want to be far away. Oh, that thing smells bad. They even repel each other. That's like electrons. They want to be as far apart as they can from all the other electrons. Even though they're making a little circle around the fire, they want to be as far apart as they can due to electron repulsions. Now, okay. However, they want to be as close as they can to the fire. So it's kind of like a two-way thing. I want to be close to the fire, but I want to be as far as I can from each other as possible. All right, so that's how they line up. But then more tacuaches come along, and they can't even fit in there. They don't even want to because it just smells so bad. It's like all this negative, negative electron cloud kind of, whatever I want to call it, kind of a horrible odor, cloud odor or something. Like, oh gosh, I don't want to be that negativity. So then the next electrons like Waches form, and they form another little. You notice that they're forming another row, or not row, but what do you want to call it? Yeah, I guess another circle, then another circle. Oh no, then another circle. My circles are getting very, I don't know, not circular, but oh well. We get the idea here. I'll just draw some electron like Waches. But all of them, all of them are good. All right, so watch carefully. There's some important stuff I'm going to bring up here. So now, here's what you want to think about. Think about the electron, or the Wache, that's all the way here at the 1, 2, 3, 4, at n equals 4. Think about this electron right here. I'm going to put a little orange around it. And think also about this electron right now. It's at n equals 1. So this n equals 1 electron, or n equals 4 electron right here. Think about these two. Which one of these, n equals 4, n equals 1, is getting more warmth from the fire right now? Like the full warmth of it. Obviously, n equals 1, it's right there. Why does n equals 4, why does this Wache not get as much fire of the nucleus, or nuclear warmth, or attraction? That's what we're looking at. Because it is being blocked by these others. So it has what's called a lower effective nuclear charge. Important word for AP students in their essays. A lower effective nuclear charge. The electron in potassium, the electron at the n equals 4 is farther away from the nucleus at n equals 4 compared to lithium, which is at n equals 2 in this case. This electron that's farther away at n equals 4 experiences a lower effective nuclear charge due to shielding. All right, and I'm going to tell you about shielding. All right, but so the symbol for effective nuclear charge is Z, then EFF, Zeph. Okay, like Jeff, a name for a guy's name, Jeff, well, Zeph, Z-E-F-F, Z, whatever. That's the effective Z. And remember, Z is like the atomic number, like a nuclear charge, but ZF will be the effective nuclear charge. So, in other words, the nuclear charge, what you normally would expect, I'll say a little bit about this. You normally expect for potassium, that's what I'm kind of talking about here. I'm trying to draw potassium, but I didn't, not perfect. It would only have one electron if it was really potassium. But potassium is positive 19 charge. Does that show up? Yeah, it kind of does. All right, and we know there are 19 electrons in potassium, all scattered through there if I did it right. Okay, well, here's the deal. Positive 19, negative 19. If every electron and every proton were perfectly paired together, then you know every electron would get have a positive 1 charge on it, and every it would all be equally divided. Everybody gets a positive 1 on each electron. If you divide 19 by 19, everybody gets one charge, 1 warmth, we'll say, from the fire. Well, but because they are being blocked, the charge that this gets on the outer electron is lower than positive 1. Another way to draw it would be this way. Do I have a space to draw this anywhere? Maybe up here at the top, I can try and do it. I'll have to draw. Let's just say that in this atom, you had a positive 19 charge, and there were no shells in between them. That all the electrons could be somehow on the outer shell. Okay, if all the electrons could be on the outer shell. Well, now, if this electron is out here, if they're all equally apart from the nucleus, the distance between there and there, pretend it's the same as there. Well, this electron will get a greater nuclear charge. That nuclear fire, it gets direct access to it. But it's being shielded. That's all the word is. It's shielded. It's being blocked. The same way that I've heard a teacher explain it this way before too. Say that there's a light in the middle, and students line up in circles around it, and another circle, another circle. Well, in a room, the ones that are standing right in the middle are going to get the brightest light. They can see each other's faces really good. But if you're way back in the back, it's real dark, and you can see, but you might can see people next to you a little bit, but it'll be a lot more shadow. You're not getting the full effect of the light. Okay? It doesn't really matter how bright the light is. You can make it as bright as you want. The ones on the inside will always experience a greater effective nuclear charge than the ones that are on the outside being blocked. So it's called the shielding effect. I told you a long story. I know you had to hear all that craziness. But the bottom line is, when you move down a group, why is, like, you can pick any two elements you want. It didn't have to be, it could have been fluorine and bromine or whatever. But tell me, each atom, where, like lithium compared to potassium. Write the short form configuration. Lithium is helium 2s1, potassium argon 4s1. What is the nuclear charge of lithium? Z equals 3, and nuclear charge is equal to positive 19 for potassium. The outermost electrons of lithium are located at n equals 2, but the outermost electron is located for potassium at n equals 4, farther from the nucleus. So one reason is because of the shielding effect, it has less attraction. Now there's also one more thing that could be thrown in if you wanted to say it as well, and it's actually very important. Coulomb's law, the equation I showed you earlier, and this applies more for this one than it did for the first one. I don't think I would really use this now that I'm going through it. I probably wouldn't say it in the same period. I wouldn't talk about Coulomb's law that much. But when you're going from one period groups going up and down, yes. Because look at the deal. They're farther away. An electron at n equals 4, the 4s1, is farther from the nucleus. I think you can say farther or further. Further from the nucleus. Further is correct. Further from the nucleus than lithium's n equals 2s1 electron. Left off my 2. So in lithium, the outermost electron at 2s1 is closer to the nucleus than the potassium's outermost electron, n equals 4. You just draw the little shells and you see, and it makes sense. And Coulomb's law, as the distance increases, as that number gets larger, if R gets larger, what's going to happen to the attraction energy? It's going to go down. If that gets larger, that goes down. So that's true. That is true for Coulomb's law. That's also true in terms of gravity, and we talked about that before as well. As I get farther and farther from the Earth, my weight will be lower and lower and lower and lower. Your weight is really just an attraction between you and the Earth, believe it or not. So the farther you get from the Earth, the lower your weight is because you're farther away. So you're allowed to use any of those concepts, but the main I would say both things. I would say that shielding. I would bring up shielding, and I would also bring up being farther from the nucleus. Like how about this? I'd say that potassium is a larger atom because its outermost electron at n equals 4 experiences shielding from the n equals 1, n equals 2, and n equals 3 layers of electrons. It experiences shielding, so it has a lower effective nuclear charge. It's held less tightly to the nucleus. It's shielded from the nucleus. And also, it is farther away from the nucleus. Okay, but for lithium, its electron is closer to the nucleus, and it only experiences shielding from the level n equals 1 layer. Its electron is closer at n equals 2. So, see, every electron is -1 charge. Every electron has the same charge. So whether you're in the outside of potassium or the outside of lithium, it doesn't matter. It's still a -1 electron. And okay, that's all that matters. And when you divide up the nucleus charge, positive 19, and the number of electrons, negative 19, if everything were equal, everybody would get a perfect positive 1 electron charge on them. Nuclear charge on them. I would say that they'd be attracted by a perfect positive 1. But with the effective nuclear charge is smaller when they're blocked by other layers. A lot of you are like, "Oh my goodness, I am listening to this stuff. What in the world?" You can also read on this in the notes and in the book, and I kind of explain it. But I have told you like just about everything I could think that you would answer in a question like that. So what you can do, and there's actually a little equation there for calculating an effective nuclear charge. which we're not going to really worry so much about it. Oh, I'll mention this thing about the... Well, I might mention something about this thing called penetration effect, but I'll get that in a second. All right, so first of all, what's your assignment right now? I told you I had to tell you at the end, unfortunately, after going through all of it. So right now, you should be able to do part 1 on this worksheet. All of part 1, which has a larger radius. So if I like to always remember which one is smaller. And if they say which one is larger, it's just the other one. But you can give the same reason. All right? Then do 1A and 2A. Yeah. And then that is all at this very moment that you can do after what I've talked about so far. That's the only thing you can do. Just Roman numeral 1 on the top of the paper. And I'm going to tell you about all the others as we move on. So it's a lot of information. But I just saw something in your notes, and I thought I would just talk about this. Well, I'll just read this to you. There was one question in here in filling up the orbitals for electron configuration. Why does the 4s fill up before the 3d? I've kind of shown you this before. In fact, I showed you this when I did quantum numbers, when I drew a 1s, then a 2s, then a 2p, then a 3s, then a 3p, and I drew it as we go. And sometimes there's overlap of orbitals. Well, the overlapping, we got to be careful with overlap. That's going to be a term they use in the bonding chapter. But there's a penetration effect, meaning some orbitals can penetrate through other orbitals. And so all it talks about is an s orbital has the strongest ability to be able to penetrate, all right? An s orbital is the best, okay? Then comes the p, then the d, then the f. So s is better than a p, better than d, better than f. So what that means is the 4s orbital is the 4s orbital has better ability to be for an electron to enter it than a d orbital, okay, than a 3d, and you know that. So as you're filling up, first go to the 4s electrons, then you go to the 3d electrons, or whatever. Okay, so the reason about that has to do with the shape of the orbital. So think of a 4s. If I drew a nucleus, and this is think about what I drew before on the other lesson. But if I drew a single 3D orbital, I told you it's kind of like this. All right, so that all of that area, that's only a single D. But then you have the 4s, and remember the 4s is going to be farther away. However, it also includes, remember, the 4s also includes all the region to the nucleus because it's at a different frequency, a different frequency matter of existence for matter. Kind of weird. Quantum. So what we're saying is, yes, the electrons would rather go into 3D first, then they would go into the 4s. Well, they would rather, if they could, but because of the ability of the 4s, and because of all the electrons that have been building up, I didn't draw the 3p and 3s, all that are in there. All this negative going on, it's more accessible to get into the 4s. And I did a little diagram like that. So 4s would be easier than the Ds would be. And if you go down the list, 1s, then 2s, 2p, 3s, 3p, 3d. Well, I'm doing it so fast. 4s, 4p, 4d, 4f. If you go through and look at all of them, I didn't draw enough of them, but you'll see sometimes the electrons, the first thing they do is they skip the 4s, then 3d. Then later you'll see that they skip to like a p orbital. Then they go to the, like an s before they go to the 3d. Like say they'll go to 4p, or no, 4f is it before they go to 6s, or well, I'll have to look at the whole thing. But they go into an s before a p, or a p before a d, or a p before an f, or a d before an f. So you'll see that happens, and that just tells you the reason why it does that is because these orbitals are able to, I really like to say the word overlap better, the other ones, but we got to be careful because overlap is used for another term in the next chapter. But 4s region can penetrate the 3D region better. I guess. Okay. All right. Well, I just brought that up because I saw it in the notes, and I probably could have been part of the next lesson. So, like, why did he do that to us? Okay, so just work on Roman numeral 1. All right, I'll see you guys.